Hi everyone. I thought I'll just spend one final lecture discussing about the power dissipation in CMOS inverters. Mainly, I want to just relook at the dynamic power dissipation and draw some small insights into it. Now, dynamic power dissipation is the power dissipation that takes place or the power dissipation of a CMOS inverter when you apply a switching input. So assume that we are feeding a clock input of frequency f, I will call it f clock, which is 1 by t, where t is the time period of this. So half the cycle, the input is 1, the other half, the input is 0. So we know that when you apply a switching input to a CMOS inverter, in one half cycle, you will charge the capacitor to VDD. The other half cycle, you will discharge the capacitor. And NMOS will discharge the capacitor to ground. Now, as far as supply is concerned, it's going to think that it's supplying a charge of CL into VDD every cycle. So therefore, the total charge it's delivered, CL into VDD is the total charge it delivers, and the average current that it's going to supply to this inverter circuit. So if you just see the CMOS inverter as a black box, then the supply will be providing an average current which is given by the charge per unit time, the charge delivered by the supply per unit time. So here we see that every cycle you are delivering a charge of Q into CL into VDD divided by the time period of this clock input. So this is the total every t seconds you're delivering CL into VDD amount of charge from supply to this capacitor. So that gives me the average current. So this is also given by CL VDD into F clock. Now we are aware of this result. Okay. Now what we need to look at it is that a very interesting result is that the average current drawn, we often call it the CVF current or the average current in a CMOS inverter, is proportional to the supply. Now what does that tell me? If you have a current that is proportional to the supply or proportional to a voltage, then that's nothing but a resistive behavior. So as far as the supply is concerned, the CMOS inverter is going to behave like a resistor. And what is the value of the resistor? So I just have to do V by I. So if I do VDD upon I average, I'm going to get 1 by CL into F clock. Okay, so this is the average resistor offered by the average resistance offered by the CMOS inverter. Now, to understand this result, we will just connect to another circuit which we are well aware of, which is the switched capacitor circuit, and then try to draw equivalence between these two. Now, let's say I have a voltage source, a DC voltage source VDD, and I'm just connecting it through a capacitor, through a switch. And this switch is controlled by the same clock input. The first cycle, when the switch is closed, the capacitor will be charged to VDD. And since there is no other discharging path, that capacitor is going to hold this voltage VDD for all time. So first cycle, if I try to plot charge as a function of time, assuming the switch has a finite resistance, the charge will be delivered with a certain time constant. Okay, so the charge will be delivered with a certain time constant. The total charge transferred from the supply to the capacitor, we can easily estimate that. So the total charge transferred from the supply in the cycle is going to be C into VDD. So that will be the total charge. And after that, once the capacitor voltage reaches VDD, even though this switch is opening and closing, there will be no transfer of charges because those two are equipotential surfaces. So you'll have a zero charge after that. So after that, if you see every cycle, the charge drawn from the supply VDD is 0. So I can say the average current drawn in the steady state is also 0. And this is not surprising. And I can say that the average resistance offered by the circuit is infinity because it's a DC input. The voltage VDD is a DC input. Therefore, for DC, capacitor offers infinite impedance. Okay, even though I'm applying a finite voltage, it's not drawing any current. So therefore, we say its impedance is infinity. It makes sense. Now, if I want to emulate a resistor using a capacitor, then all I need to do is to remove this charge storage capacity of a capacitor. So because the capacitor is able to hold on to this charge VDD even when the switch is open, so that's why when the switch is connected, when the switch is turned on in the next cycle, the voltage, there is no charge demanded from this voltage source VDD. But if I can turn off, or if I can discharge this charge in the one half of the cycle, then when the next clock cycle arrives, the capacitor voltage is going to be 0. So immediately the charge will be transferred from the supply to the capacitor. So then we add another switch controlled by the other phase. So in one phase, the switch is on, the switch charging the capacitor is on. So this capacitor is open. The other phase, the discharging switch is on, the charging switch is off. Now if I do that, what am I doing here is I am trying to remove the charge storing capacity of the memory property of a capacitor. The capacitor can hold charges. By adding a switch in parallel to the capacitor, I'm discharging the charge that was stored, or that was transferred from supply to the capacitor in the positive cycle. Now if I do that, now I'm emulating a resistive behavior, because a resistor is a circuit without memory. So if you remove the voltage across it, then the current will go, or if you open the switch, so if I have a voltage source connected through a switch, so the moment the switch is open, the voltage across the resistor is going to come to 0. Okay, so that's what I'm trying to emulate here as well. But since it's not an exact equivalent circuit, on an average, if I assume that the switch discharging resistances, or the switch resistance is negligibly small, then I can assume that I can emulate the behavior of a resistor. So now if you see, in one half of the cycle, the voltage source will transfer a charge of C into VDD, and in the other half, the voltage source does not transfer any charge. And when the next cycle comes, in this cycle, this switch turns on and discharges the capacitor. So the voltage across the capacitor will be 0. And when the next cycle comes, the capacitor will again be charged to VDD by the DC voltage source. So now every cycle you're delivering a charge of value equals CL into VDD. Every cycle you're delivering this charge. Okay, so every cycle, since you're delivering this charge, so then I can estimate the average current. So the average current is the rate at which the charge is transferred, and here we see that we are transferring a charge of CL into VDD every t seconds. So divided by t, I get the average current. So from that, I can estimate the equivalent resistance that this circuit offers. So if you see this combination of capacitor and switches offers an equivalent resistance whose value is given by 1 by f clock into CL. Okay, and we are well aware of this, which is what we call the switched capacitor circuit. So using a combination of switches and a capacitor, I can emulate a resistive behavior. Now we will go back to our inverter circuit. Now if you see a CMOS inverter, and I'm going to feed a positive clock cycle, or a clock input to the CMOS inverter. In one half of the clock cycle, PMOS conducts, and in the other half, NMOS conducts and discharges the capacitor. I can just redraw the circuit this way. So I'm connecting V in through the PMOS device to the capacitor. So this is the charging path. So whenever V in is 0, you're going to charge the capacitor, and this NMOS is open. And when V in is high, the PMOS switch will open and NMOS will discharge the capacitor. So what you have done effectively is we have emulated, we have just, or rather I can say the CMOS inverter can be reduced to a switched capacitor circuit. So I'll call this as phi bar and phi. So when I say phi bar, it simply means when phi is 0, the switch is on, or when the clock is 0, the switch is on. So I've just redrawn the CMOS inverter differently here, and that simply reduces to a switched capacitor circuit. So as far as the supply is concerned, the CMOS inverter with a load capacitor is going to look like a switched capacitor circuit. and therefore it's going to offer a resistive load, and that equivalent resistive load is given by 1 by CL into F clock. So if I increase the switching frequency, if I increase my clock frequency, then it's going to offer lower and lower resistor, which means you're going to draw more and more current. More and more average current will just increase linearly. Okay, so that's one very interesting property. Now, where do we use this as engineers? Typically, where this equivalent resistance matters to us. Where it matters to us is especially for analog engineers who are designing, say, voltage regulator circuits. So typically, for voltage regulator engineers, they are mostly feedback systems. So you are used to analyzing the small signal behavior of this LDO. So we are used to using terms like phase margin, gain margin, and DC gain, and all those terms. So when we are going to do that, since inverter is a large signal circuit, which is switching behavior, we will not be able to do the conventional AC analysis. Now to do that, what we will do is we will replace this inverter with its equivalent resistance. Okay, on an average, we know the inverter is going to look like it's going to offer a switched capacitor load or an equivalent resistive load. So therefore, I can just model this CMOS inverter. So when I say CMOS inverter, I'm just simplifying the circuit. Generally, any digital circuit with switching inputs. So you have a complex digital circuit, and the complex digital circuit, if you know the power, typically you can reduce it to a CV of kind of an average current. So which means you can estimate its equivalent resistance. And that equivalent resistance is what you will use in your circuit model when you're designing your LDO, and then we can perform all the conventional AC analysis to estimate its stability and all of that. Okay, so that's it. So that's a very interesting point. Often I felt was not discussed in textbooks. So which is why I thought I'll just briefly discuss this as a switching CMOS inverter circuit. Okay, emulates or looks like a switched capacitor circuit as far as the supply is concerned. And therefore, as the supply is concerned, it's going to look like a resistive load as far as the supply. And when you see from the supply, it's going to look like a resistive load. Okay, thank you.